Hello everybody, welcome to lecture number 10. Today our only goal is to learn the fundamental theorem of calculus, the FTC. This is what Newton discovered in the 1660s, like 1660 something. And then Leibniz also figured out independently in the 1670s, and that's why those two get called the discoverers of calculus, because they discovered this theorem right here, which is how derivatives and integrals relate to each other. So again, Newton did it first, but Leibniz published it first, whole bunch of history there. Okay, so what the theorem says. First off, let your function f be continuous in the closed interval ab. Part 1 of this theorem says if you define the function big f of x as the integral from a to x of f dt, then big F prime is small f for all x in the interval a to b. What this says is that if your function is an integral, the derivative will undo the integral. So essentially this says that integration and differentiation are inverse operations. That's the big message in part 1. Inverse operations. Integration and differentiation are inverse operations. Because when you differentiate the integral, they cancel out and you're just left with the function inside. This was the big deal. Part 2, especially the way that I prove them, part 2 is just a consequence of part 1. Part 1 is the big deal. Part 2 is the consequence. Part 2 says that if g is any antiderivative of f, then the integral from a to b of f is g of b minus g of a. This is the more useful part for us, right? Because this gives us an easy way to compute definite integrals. But in terms of the mathematical significance or the breakthrough, part 1 is the big deal. And part 2 is by no means intuitive. Because part 2 says if you want to find the area underneath the function f, just find a function whose derivative is f, which doesn't seem to match. I'll say it one more time. This says if you want to find the area underneath f, just find yourself a function that differentiates to f. So it's kind of this weird question how to find slope. You have to do the opposite of area, which kind of plays right along with this, that integration and differentiation are inverse operations. So first we'll prove these. We'll do a formal proof first, and then we'll explain them a bit more informally. We'll prove part 1. Actually, I'll get myself a new piece of paper. One more side note before we get into the proof. Newton and Leibniz figured this out in the 1660s, 1670s, but it was a French mathematician, Joseph Lagrange. He was the one that proved it for the first time in the 1700s. So these two knew that it was true just geometrically, but Lagrange was the first formal proof that this thing actually worked. Okay, here's the proof of part 1. So first off, let some function big f of x equal the integral from a to x of f of t dt such that small f is continuous on an interval that contains both those points. Right, so this function big F gives you the area underneath this curve from a to x, because integrals give you area. This is the area from a to x. We want to find f prime. And we know from the definition of the derivative that big F prime is the limit as delta x approaches 0 of big f of x plus delta x minus big F of x over delta x. Right, the derivative is just the slope between 2 points on the curve as those 2 points become infinitely close to each other. We then plug those 2 inputs into our function. So big F prime is the limit as delta x approaches 0 of the integral from a to x plus delta x minus big F of x, which is the integral from a to x, all over delta x. And so we get to that step. For our next step, let's see what this actually looks like. So if we had some continuous function f of t, right, this integral gives us the area between that function and that axis from a until some point x plus delta x. So we'll say here's a, here's x plus delta x. So the first integral gives us this area, or this space, this amount of space between the curve and the x-axis, or the t-axis, I should say. And then we subtract the area underneath this curve from a until x. The area from a until x is this part right here. What you're left with after you do the whole area from a to x plus delta x, and then you take away the area from a to x, is this region right there, which is the integral from x to x plus delta x f of t dt. So we rewrite our derivative big F prime as the limit as delta x approaches 0 of just the integral from x to x plus delta x f of t dt over delta x. And then we go one more step and we write that like this. Instead of dividing by delta x, multiply by the reciprocal. Okay, now from here we use the result of the average value of a function. We derived this at the end of our previous lecture. I'll just write down the result really fast. So the average value of f on the interval a to b is, we'll call it y bar, and it's 1 over b minus a times the integral from a to b f of x dx. And if f is continuous on the interval a to b, then the function is guaranteed to equal y bar at some point in the interval. So to recap that, we figured this all out at the end of our last tape lecture. The average value of a function on some closed interval is 1 over the length of the interval times the integral from a to b of that function. And if your function is continuous, then that average value is guaranteed to happen for some x value in the interval. So t bar is the x value, which when you plug it into f gives you the average value. Why we care about this is look at this integral right here. This is 1 over delta x times the integral from x to x plus delta x. This is the average value of this function f of t from x to x plus delta x. So this is the average value, and this average value we'll call f of t bar, because since f is continuous, way back up here, f is continuous, it is guaranteed that our function f equals this average value at some point in the interval. So, continuing our proof, so let's say let 1 over delta x times the integral from x to x plus delta x f of t dt equal f of t bar for some value t bar in the interval x to x plus delta x. And again, this t bar is the x value that you plug into this to get the average value. Well, this allows us to rewrite big F prime. Instead of being the limit of this average value expression, is just the limit of the average value, f of t bar. But one more fact. Now t bar is in the interval x to x plus delta x. So what happens when delta x goes to 0? Well, if delta x is going to 0, this interval is shrinking. And since t bar is in that interval, it must be approaching that fixed endpoint. Right? As delta x approaches 0, this interval just shrinks down to x, and t bar, which is in the interval, must also approach x. So that means that big F prime can be expressed as a limit as t bar approaches x of f of t bar. Because delta x approaching 0 implies that t bar is approaching x. And now we have it, because f is a continuous function, which means it's well behaved, which means we can just plug this value into the variable. Therefore, these three dots mean therefore, big F prime equals f of x. Done. QED if you want to finish a proof in the old school way, which just means that we just showed that which we were trying to prove. Now that proof might need a couple viewings. You might have to rewind and watch it again. But even if you watch it more than a few times, this does not give you a good feel for why it's true. This just shows us that with the properties that we have learned, that if you differentiate the integral, they cancel out and they leave you with just the inside function. Right? This just says that when you differentiate the integral, that the derivative and the integral undo each other, you just get the function inside. Although not until you've plugged in your variable. Okay, which we'll explain that too. Okay, so that's the proof of part 1. That was the huge deal. Now let's prove part 2. So part 2 is the part that is the most useful to us because it gives us a nice, much quicker way to compute definite integrals. But as I mentioned earlier in the video, it's just a consequence of part 1. So let's do it though. So let's say that we have some function big F of x, which is the integral from a to x of f of t dt. For a continuous function f is still continuous. We just showed in part 1, so I'll say by part 1, we just showed that big F prime equals f of x, which means that big F is an antiderivative of small f on the interval a to v. If big F is an antiderivative, that means that so is big G, where big G is just different from big F by a constant. Why this is true? Well, think about it. If big F differentiates to be small f, then so does big G. Just to kind of restate that, this means that big G prime also differentiates to f, which means that big G is an antiderivative. So big G is also an antiderivative of small f. Now let's see what this means for us. If we rewrite this, we get big F of x is big G of x minus c. Try to subtract over the c. At x equals a, we have two expressions for big F. From the first definition of big F, we have that big F of a equals the integral from a until a, because the variable is the upper bound on your integral. But that gives us 0. The area underneath f from a to a, you don't go anywhere, so the area is 0. We also have, from the second expression for f of x's definition, that big F of a is just big G of a minus c. Now, since f of a equals both those things, those two must be equivalent to each other. And if G of a minus c equals 0, that means that c has to equal G of a. Right? That's the only way for G of a minus c to equal 0, is if c and G of a are equal. That means that big F of x is big G of x minus G of a. Also, at x equals b, which is the right endpoints of our interval. At x equals b, big F of b, if we use the first definition of big F, is the integral from a to b. If we use the second definition, which is right here, big F of b equals big G of b, because that's the variable, minus big G of a. And there we have it. We just showed that the integral from a to b has got to be the antiderivative at b minus the antiderivative at a. Later in this lecture, we'll do a bunch of examples of this, but it gives us a much easier way to do definite integrals. No more Riemann sums for us, no more limits, no more formulas. It's just that result right there. And there are other ways to prove this. You could use the mean value theorem. Actually, I should have mentioned it. The mean value theorem was in here. I just didn't reference it. But the mean value theorem did kind of make all the stuff work. So again, those are the formal proofs of this huge theorem in calculus. So next, let's check out the informal explanations for why these actually make sense, these results.